Okay, we're at lecture 8 today. The task today is to hopefully fully look at parametric equations. We'll have a function, not a function of x, like y equals f of x, but we'll have y as a function of t and x as a function of t or some other parameter. We'll look at parametric equations, and we'll revisit those throughout the semester, and you'll also revisit them in 241 as well. Before class, there was a statement made about possibly wanting to look at an inverse problem. Is it a web-assigned problem? Okay, so let's look at that first. That way we can kind of judge how much time we have left for parametric equations. So, goal 1.7 in the text, parametric curves or parametric equations. What are they like? What are some kind of common equations? And then how can you eliminate the parameter and get y as a function of x, if that's what we need? Okay, web-assigned question first. Kent, what is that?
The equation was 6x minus 1.
Y equals 6x minus 1? Okay.
Over 2x plus 5.
2x plus 5?
Yeah.
Okay. And this is the original f of x. And we want f inverse. Anything else? Like domains, any of that stuff? That's a possible test question, so why don't I add that in? What's the domain of the original f of x? Okay, negative 5 halves, right? Any real number except x equals negative 5 halves? And we could put that in interval notation, but that's basically what we're dealing with as far as the domain. If you were to graph this, what would you expect there to be at or near this x value? Asymptote. Okay. Not only is this completely undefined at negative 5 halves, it kind of goes crazy near negative 5 halves. So we should expect this to be a vertical boundary, a vertical asymptote. If you are asked for the range, you might want to wait on the range till we find the inverse. And what can we use about the inverse to be the range of the original?
The range of the inverse is the domain of
Okay, that's exactly right. So the range of this one, of f of x, ought to be the domain of f inverse, right? So if that's not real obvious what the range is, just kind of save that till we can look at the inverse. So find f inverse. So here's our so-called original function. What do we do with that? Switch x and y. X is the same thing as x over 1, so we could cross multiply. Somebody that had success with this problem, tell me what you did from this point.
Multiply through x.
Okay, distribute the x. So 2xy plus 5x. So we've interchanged x and y, and we've done a little algebra. Now what's kind of the next major step of finding an inverse?
Put all the y's to one side.
Okay, and the purpose of putting all the y's to one side would be?
So you can
Right, so we can kind of isolate y eventually. All right, so 6y is already here. Let's leave that there. Bring this over as a minus 2xy. Take the minus 1 to the other side by adding 1 to both sides. Does that look right? So we've got all the terms that have y in them on one side. Casey, you said what now we want to do with y?
take out the y and do y. Let's see, 6 minus 2x.
And divide both sides by 6 minus 2x. So that ought to be F inverse. What's the domain of F inverse? Reals, what? X can equal 3. So the domain of the inverse ought to be the range of the original, right? So all y's up here that are real except for 3, you're not going to get 3. Tell me what that would be up here. Any real number, y not equal to 3. So visually, what is y equals 3 on the original function? Horizontal asymptote, right? So we have a vertical asymptote and a horizontal asymptote here. The domain down here, this ought to be a vertical asymptote at x equals 3. And the range here ought to be what? All reals. Y could be anything except negative 5 halves. Is that all right? Does that work okay? Anything else that's pending or burning on the topic of inverse before we embark on parametric equations? So I bet you that this was the kind of the issue, is multiplying everything out, getting all the terms that have y on one side, purpose being to isolate y. And I have asked a question like this. I told you by the time we get to test 1, you're going to pretty much know test 1 because I'm going to give you hints all along. I have asked a question like this before on a test. And I've also included this stuff. Find the domain, find the range of the original, find the domain and range of the inverse. Okay to leave this one. Okay, let's talk about parametric. Functions, parametric equations. Really, a lot of these turn out to be non-functions, so we better say equations. So we're going to have things defined in terms of a parameter. So we could have x, let's say, as a function of t, and y also described or defined as, let me call it something else, some other function of t, some g of t. Why would you want x described or defined in terms of some other letter? Why would you want y defined or described in terms of some other letter? Maybe they're both functions of time. That x is described or defined as a function of time. So we know where the x coordinate is based on some function that says you plug it in, t equals 3 seconds, t equals 5 seconds, you plug it in, it tells you what x is. Same thing with y. Now it is possible, it can get kind of ugly sometimes, but we can eliminate the parameter. The parameter is kind of the third variable, in this case t, so we can have an equation of x in terms of y. But it's possible to go ahead and plot points, determine where it is, give it some kind of direction based on how we start from left to right, without necessarily finding a function of y in terms of x. So instead of just kind of plotting points and generating, plugging in an x and generating a y, we're going to have some set of points, numbers, hopefully, that are, in this case, positions, if t happens to be time. All right, let's look at this. This is a pretty simple example to start with. Let's say x is t squared, and y is 6 minus 3t. So x in terms of t, y in terms of t, so our parameter is t. We could, which we will at the end of this problem, eliminate the parameter and find y in terms of x, or x in terms of y, kind of depending on what we think is more appropriate. So if I were plotting points, I'll probably plug in a t value first. and then see what x is and see what y is at that particular value for t. And I'll try to kind of develop a left to right point plotting mentality, at least in terms of t. So I'll let t start at -2. I'm just picking a value, some negative value, and kind of progressing to the right. So if t is -2, what is x? 4. What is y? 12. Not that that's the starting point, but that's our starting point as we plot points here from negative values of t all the way up to positive values of t. Let's keep going down the line. X is what when t is -1? Y is 9. 0. X is t squared, so it's also 0. Y is 0. Excuse me, t is 0. Y is 6. I don't know if it appears that this is any particular pattern to you. We'll plot these in a moment. X is 1. Excuse me, t is 1. X is also 1, right? And y is 3. And our last value, just to see if we can get an idea of where this thing is in the plane, when t is 2, x is 4, and y is 0. So you can plot a lot more points. Let's see where these points are in the plane. Now we are, because we've got a lot of letters going on, x and y and a t, this is our x value, this is our y value. Now we have found them in terms of a parameter t, but that's not on the coordinate plane anywhere. So we're picking off points 4, 12, 1, 9, 0, 6, and so on. So 4, 12, 1, 9, 0, 6. So I'm going to go ahead and give this thing a little direction here. That's kind of how we started and where it's headed. I don't know if you can tell what it is. It's hard to tell at this point. At least it's a function to this point. I think we're going to lose that property. 1, 3, and 4, 0. So it looks like it's parabolic. It looks that way to me. It's clearly not a function. Let's see if we can eliminate the parameter, get rid of t, and see if we think it looks like it ought to look in terms of the equation. And we could plot more points, but this is a general idea of where it is in the plane, and kind of how it progresses from negative values of t to 0 to positive values of t. That seems to be the direction. Let's take these equations. Let's take y. We could do this either way, actually. But let's take y and solve it for t. So we could subtract 6 from both sides, divide both sides by -3, or multiply by -1/3. All right, so there's our t value. The thing that makes this a little bit nice is all we have to do is plug it in here and square it, right? There's our t value. So x equals t squared. We now have something that t is equal to. There's some kind of high-pitched sound. Leonard, I don't know what that is. Do you hear that? Does everybody hear that? I don't know if it's the air conditioner or first time I've noticed it today. Have you noticed it before? Anybody? So we're going to square that. Negative 1/3 squared is... Actually, let's just leave that alone, and let's see if we think it looks like... well, let's rewrite it. The whole thing squared, right? Because that is t. We want to square the whole thing. Let's go ahead and call this 1/9. All right, so with that equation, so the parameter's been eliminated, does that look like what we think it would look like? Does that look like a parabola that's a non-function? Right? X is to the first. Y is squared. Kind of has that parabolic look to it. Now how about this y minus 6? Normally when we see like x minus 3, the net effect is to shift it right 3. How about y minus 6? Where should that shift it? Up 6. Does that look good? Okay, that seems to be right. There's the vertex. And the fact that it's got positive 1/9 for the coefficient of the quadratic term means it ought to open either up if it were y in terms of x. Now it's x in terms of y. It ought to open to the right. So this means up 6 units, which appears to be true. And this positive 1/9 says it ought to open to the right, which appears to be true. So we plotted it in terms of the parameter, but now that we eliminated the parameter, it seems to be that x in terms of y seems to be valid according to the picture that we have. Any questions on that? All right, let's get some trig involved. Yay. Try to not let a day go by without looking at some trig in some way, shape, or form. So let's say that we have, on the next example, x equals cosine of t, and y equals sine of t. And let's let the parameter t go from 0 to 2 pi. Does that ring a bell at all? X equals cosine of t, y equals sine of t. Not ringing any bells this morning?
Absolutely not.
Absolutely no bells are ringing. Okay, let's see if we can make them come alive. Okay? Let me bring this equation up. Everybody recognize that. What would that be? X squared plus y squared equals 1. That's a circle, right? Circle with center at the origin. And a radius of 1, right? We give that a nice little name and call it the unit circle, right? Could I make substitutions here for x if I put in cosine of theta, cosine of t, and for y, plug in sine of t, and is that a legitimate equation? It is, okay? So these parametric equations, x in terms of t, y in terms of t, appear to be the unit circle, right? And I think if you kind of dig back into your trig memory bank, you'll remember that x equals r cosine theta. Remember that? And y equals r sine theta. Kind of the same thing. R in this case would be 1, which would be the radius of the circle because it's a unit circle. So we should expect it to be the unit circle. I don't know, we could plot a couple points just to validate. So the parameter is supposed to go from 0 to 2 pi. Let's plug in a few values, kind of refresh a few trig values. So 0, let's plug in pi over 6, pi over 4, pi over 3. You were hoping I would skip all those. No such luck this morning. When t is 0, x equals cosine 0. What's that? 1. Y equals sine of 0. 0. So there's our first Cartesian point, 1, 0. How about pi over 6? What's the cosine of pi over 6? 1/2? No. Square root of 3 over 2? Yes?
That sounds right.
Sounds right?
Yeah.
Okay. Cosine, remember, starts at 1 and then decreases, right? Kind of does that kind of deal. And sine starts at 0 and does that through its first full cycle, which is all we're looking at, 0 to 2 pi. So we've got the cosine. It should be on its way down from 1. Square root of 3 over 2. Agree on that? Which is about 0.866 if you want to check it out. Sine of pi over 6. Sine starts at 0, so now it's going to start its climb. 1/2. Pi over 4, which is the equivalent of right midway through the quadrant, so a 45 degree. So sine and cosine ought to be the same. Square root of 2 over 2. In both cases, it's a little more than 7/10, 0.707. Pi over 3. Cosine now is on its way down. 1/2. Sine is on its way up. And pi over 2, cosine of pi over 2, 0, and sine of pi over 2 is 1. And if we were to plot those points, you would see that these points actually do kind of begin to create that unit circle. Let's see if we can get a real quick sketch here. So 1, 0, we're starting here. Square root of 3 over 2, 1/2. Square root of 2 over 2, which is about 7/10, somewhere right in here. 1/2. Square root of 3 over 2. And 0, 1. So with the point plotting where we started, we're here on this unit circle, and we've now come to this point. We've gone through pi over 2. As far as our parameter is concerned, we're supposed to carry through with the parameter to 0 to 2 pi. Anybody need to see any more points? Everybody believe that we're going to come up with a unit circle here. You would see that as the points would work their way around, we're going to get a unit circle, which isn't a mystery if you look at the original. So what is the Cartesian equation? This is it, right? X squared plus y squared equals 1. We can eliminate the parameter and have a function, not a function, an equation in terms of x and y. X squared plus y squared equals 1. Questions or issues with that one? Okay, third example. Let's say this time that x equals sine squared. This is a little, seems overly simplified. It's kind of a strange little example. So we have x in terms of theta, could be t, y in terms of theta, and we just had that sine squared of theta plus cosine squared of theta equals 1. But it's not the same thing. It's not a circle, because sine squared is x, right? So for sine squared, I can plug in x. For cosine squared, I can plug in y. So we get x plus y equals 1. That's not a unit circle. What is that? That's a line. Okay? And you could say that's the line y equals what? Negative x plus 1. Question is, do we have the entire line? This is a little strange. Maybe you can go back to the parametric definitions and tell me, are we going to have the entire line? If we had the entire line, it would look something like this. Y-intercept is 1, and the slope is negative 1. So it would look something like that. We're not going to get the whole line. Which part of this line are we going to get and why?
From 0 to 2 pi because of a strict function.
Okay. So we're going to get some repetition after that, right? So we don't need to plug in any more values. Tell me about x. If it's something squared, what's x all the time? Positive, or at the very worst or least, 0, right? So we're going to take the sine of something and square it, and that's going to be our x value, 0 or positive. We're going to take the cosine of something and square it. So the y value is also 0 or positive. So do we have the entire line? We have just the first quadrant piece of this. So we're not going to be able to generate that point, right? Because they have what? Negative x values? We're not going to get any negative x values. These have what? Negative y values. We're not going to be able to generate those. So the net graph, if you were to plot points, it kind of goes back and forth from here to here. Comes this direction as you're plotting points, and then it comes back this direction. So it just kind of goes back and forth and retraces this line segment, which you would not guess that from this equation, x plus y equals 1. You'd say that's the whole line, so you got to go all the way back to the parametric equations. We don't get the whole line, we just get a line segment. Questions or issues with that? All right, the last example for this section. Good, we might actually get a little farther than what I planned. That'd be wonderful. Is the idea of a cycloid. So let's take this topic of a cycloid. Let's look at the equations. If we were a little better timing-wise in this class, and if I didn't have us kind of behind where we should be, we would develop the equations. But we'll plot enough points, I think, where you can see that the equations, in fact, do work. That is an R. So there's our parametric equations in terms of theta. So what is a cycloid? Anybody ever worked or done anything with a cycloid before that you know how a cycloid is formed or how it gets traced out. Anybody? Cycloid? Might look familiar as we talk about it. It is a curve that's traced out by taking a point on a circle and basically rolling that circle down the number line. Okay?
Does that say theta is equal to all reals? Or
Yes.
less than theta?
Theta is an element of the reals. So here is a cycloid. Great props today. Okay? Paper plate. The dot is the point that we're tracing. Okay? So if we start it at the axis, okay, that's where our cycloid is going to begin at the origin. So if we would put in 0 in here, we're going to get 0, 0. Now, pay attention to the black dot as I roll this along. The black dot is coming up, right? I roll this thing along, and the black dot now is at its peak. It's never going to be more than that, higher than that. So that is basically the diameter of this circle. And as I continue to roll this, it goes back down toward the origin, right? So if you want to kind of trace that, starts at the origin, climbs up as theta is progressing. It gets up to the peak, and then it goes back down, and then doesn't that process start all over again? So here is kind of how the equation is going to be developed in terms of what theta is. Theta is this angle by which we're going to kind of roll this. And as we roll this, here's our point on the paper plate. So it starts here, and as you roll this, it is tracked along this path. This is our path called a cycloid as you roll the circle through larger and larger values of theta. So this is in your book. You can look on page 78 if you want to see this diagram, and if you want to justify all these equations in terms of line segments that are pictured on this diagram in terms of x values and y values. So here's our x value here, and here's the y value here. You can look at segments. Now, what does this look like as we kind of continue this process? I also have that, if I can find it. So as we roll this thing, there's the dot. It rolls up to the peak, kind of, which is the diameter or twice the radius here, and then it comes back down, and then it starts that process all over again. So that's what a cycloid looks like. And these are the parametric equations. So now that I've described it, and you've kind of seen what it looks like, have you done anything in a math or science class prior to today with a cycloid? Okay? Something possibly completely new for most of you. If we were to plot a few points, I don't want to plot a bunch of them. So we could start at 0. R is the radius. Let's just assign what we want the radius to be. Let's just give it a number. Let's say that R is 4, just for example purposes. The radius of this plate is 4 inches. So if R is 4, we would have theta, which is 0, minus the sine of theta, sine of 0. 0 minus 0 is 0, times that is 0. We know what the starting point is. We're just validating it. If theta is 0, the cosine of theta, cosine of 0 is 1. 1 minus 1 is 0. 0 times that. So we know where it started. Starts at the origin. Okay, let's avoid a couple of intermediate values and roll on to pi over 2. So we've rolled it through this central angle of pi over 2 radians. So that'd be pi over 2 minus the sine of pi over 2. What's the sine of pi over 2? That'd be 1. And pi over 2 itself is the number pi, 3.14 approximately, divided by 2, which is about 1.57. Does that sound right? So 1.57 minus 1 would be 0.57. Somebody has a calculator. What's that times 4? 4 times, what is it? 2.3, roughly. All right, let's plug in pi over 2 here. Cosine of pi over 2 is 0. 1 minus 0 is 1. So we're at 4, right? R is 4. Take it through now another pi over 2, so we're over to pi radians. Pi minus the sine of pi. Well, the sine of pi is 0. I can tell you're loving the trig. Okay, that's 0. So it's pi minus 0, which is just pi. So that'd be 4 times pi. I'll just go ahead and write that. We could get a decimal equivalent of that. And again, at pi, cosine of pi is -1, right? Get that mental picture going of cosine. There's where we're talking about, right? At pi. Kind of halfway through that process, we're down to -1. 1 minus -1 is 2 times r is, in this case, 8. And we could plot points. You'll see if you plot these points, starting here, 2.34. And then 4 pi. What is 4 pi? Somebody on a calculator? 12.56. And then we're up, what, 8? Does that look like what we thought it was going to look like? Right? Is that the peak? It's got to be the peak, right? Because when we start it, it's at the bottom. When we roll this thing along till we get the black dot at the top, wasn't this 4? Radius of 4? So the 2 radii make up the diameter, which is 8. So that's got to be its peak. So we would see this thing start to decline. Now, another reason why it ought to be at its peak is because we just plotted the point pi, which is, we start the repetition cycle. Aren't we halfway through the kind of the cycle that sine and cosine begin to repeat values? The period is 2 pi, and we're halfway through that with pi. So we should expect it to be at its peak. But this is a cycloid. So for some of you, most of you, I think this is your first encounter with what a cycloid is. Do you see what a mess this would be to solve for y, to solve for theta in terms of y and then plug it into the other equation? This is a mess. This is a real mess to try to get the Cartesian coordinate. So we're not going to do that all the time. We'll do it when it seems like it can be done fairly readily, but here's one where we're not. We're not going to solve it for theta in terms of y and then plug it into the other equation. Not really wonderfully fun adventure. All right, now what are we going to see later in calculus that this might be handy for us to have parametric equations or handed parametric equations? Let's say that we have x in terms of theta or t or some parameter. have y in terms of theta or t or some other parameter. Okay, we've got parametric equations. We want, this may not make a whole lot of sense at this point in time, but in a couple weeks, we're going to be finding this thing which is called dy over dx, or the derivative of y with respect to x. It's kind of what half of, maybe a little bit more than half of this particular course is all about, is finding and using and applying derivatives. This is a derivative. So we want that. Now, maybe we have an ugly equation like we just had, that it's very difficult to get at y in terms of x. But we have x in terms of theta and y in terms of theta. We're going to be able to find the derivative of y with respect to theta, derivative of x with respect to theta, and that's going to give us what we want without having to do battle with this substitution and solving for y in terms of x. We can leave it, use the parametric equation to find that derivative, use the parametric equation to find that derivative. Can you see algebraically it kind of looks like the d thetas drop out, right? And you'd be left with dy over dx. If you multiplied the top by d theta, you multiplied the bottom by d theta, that would give us what we want. So that's going to actually be pretty valuable. Parametric equations is not having to eliminate the parameter and just taking what's been handed to us, finding what it is that we want. But that is a little bit later. All right, let's go into Chapter 2. Talks about the tangent and velocity problems. So now we're starting this kind of mindset that we want to develop in the first half of calculus, that we want to deal with how curves are changing, but at any one specific instant. So with lines, we construct a line in the plane, and we have the equation of that line. It has a fixed slope. So whether I take this point and this point, find the slope, this second point and a third point, this point and any one of those three, it doesn't matter what points I choose, the slope is fixed. That's why it's a line. It's constant. So it might be 1/8, which means for every pair of points you pick, rise over run is somehow or another going to reduce to 1/8. It's fixed. Curves also have slope. So we'll look at slopes of curves in a couple of different ways. So let's say the curve looks like this. So we might look at what has happened from this point to this point. So we are dealing with a line that connects those 2 points. So the terminology used here, and I think you've probably used this terminology before, is the slope of the secant line. Secant, probably you saw in high school geometry when you talked about a circle and a line that sliced through a circle and made 2 points of contact. That's probably where you saw the word secant the first time. That is a secant line. So we might want to see the slope of the secant line. Is that valuable information? Yeah, maybe. It tells us on average what happened as we went from here to here. It doesn't really explain what's going on here, nor any of these individual points, but it does tell us that on average the trend on this function was to kind of go up, right?
If it's a secant, it has to be 2 points.
2 points of contact.
Okay.
So we've got the curve and we've got some starting point, some initial point, and some point later on down the line. Now we might also want to talk about what's going on at a specific instant, okay? So I mean, what we might want to say, at this point, what's going on? There we go. Slope of a tangent. And that has validity also. That has some merit. In fact, it might, in some cases, have more merit. We may want to know exactly what's going on here. What's the tendency at this one point? Or what's the trend or tendency at this one point right here? So both slopes are valid. They both give us different information. But with curves, we need to be prepared to talk about slopes as well. They just have variable slope. This slope is possibly different from this one, which is potentially different from the slope of the tangent line right here. So we're going to have different slopes. So when we talk about, and this is kind of my terminology, when you see M with a little subscripted SEC, we're talking about the slope of the secant. So this means that we have 2 points. And we use our old-fashioned definition description of slope. So we would expect the slope to be difference of y's over difference of x's. This gets a little tricky now when we start talking about the slope of the tangent, because here we only have 1 point, which basically throws this out the window, right? If we don't have 2 points, how can we have y2 and y1? How can we have x2 and x1? We've only got 1 point. So we have to come up with another way of finding slope, and this uses limits. So this is going to be very rough. But let's do just a minute or two of this, and then we'll stop and pick up from this point tomorrow. Let's say that the goal is to find out what's going on at this point right here. I'm going to give that point a name. Let's suppose that it's over here x units, and it's up f of x units. So that's the goal, to see what's happening at this point. With 1 point, however, we can't use our old-fashioned definition of slope. So what we do is we go to a second point. Now, I don't want to be actually this far away from my first point, but if I start closer, it's going to get cluttered in a hurry. So let's say we move over h units, and we get to another point. So if we were already over x units and we moved over h more, we're now where? Okay, x plus h. And its corresponding y value is the f of x plus h. So there's our 2 points. So if we wanted the slope of the secant, we could start with that. I know this isn't the ultimate goal, but it's where we're going to start. It would be the y value here minus the y value here all over the x value where I started. I have to go back to the same point minus the x value over here.
But then the x is just cancel.
Yes, in the denominator, we aren't taking the f of anything, and we don't know what the f is. But in the denominator, it's just x plus h. Drop out the x, so we should have just h. So that's the slope of the secant. All right, now to kind of take a few seconds to say where we're headed, and we'll start class tomorrow. If I really want the slope of the tangent, what do I have to allow to happen on this picture? I really want my 2 points to not be so far apart. I want my 2 points to get closer together. So maybe I'll want my second point to be here. Actually, that's too far away. I'd like it to be a whole lot closer. I'd like it to be here. And as I take my second point and I bring it closer to my first point, what is actually happening on this diagram?
It's becoming the same point.
Okay, the 2 points are becoming the same point. Isn't it true that h is getting smaller?
Yes.
Is that correct? So we want, and we'll start with this tomorrow, we want to take a limit as h approaches 0. Then we can get from this thing called a secant to this other thing called a tangent. So we'll start class with that tomorrow. Have a good afternoon.